Our last speaker for the day is going to be Junaid Muzammil. Junaid is currently serving as a tech lead database reality at Yelp UK and will therefore be joining us remotely. His interest revolves around distributed data stores such as Cassandra and Zookeeper, emphasizing their interactions and automation. So let's see what we can learn from Junaid today. His talk is going to be a recorded session, but he'll be taking the question and answers live.
Assalamu alaikum and hello everyone. Welcome to PyCon 2024 and I hope you are having a great time today. I'm extremely excited speaking again at this beautiful conference. The last time I was in 2019, I was also part of it. And today I would like to talk about PySpark and mainly we'll try to focus on the technology agnostic aspects of it. So starting off with a bit of introduction about myself, who am I and what I do. Currently, I'm a software engineer in the database reliability engineering group at Yelp. I'm based in London. Overall, I have more than 12 years of experience working with different open source technologies. I started my career as an embedded software engineer and then later moved into data engineering and platform engineering roles. I'm extremely passionate about data stores, specifically Cassandra and ElasticSearch, so you will find quite some references to those inside my talk. And as an engineer, I love solving problems related to these complex systems through coding and a programmatic approach. Outside of work, I like going out on long walks and exploring new places. Yeah. So, as we'll be looking into the technology agnostic sides of PySpark, a question comes into mind that is it really essential to be technology agnostic in the current age? To answer this question, maybe I'll try to go through a journey, what I have learned over my career. When I started back in early 2011, the data store landscape only had a few players. Mostly they belong to the relational databases. You would find presence from Oracle, MySQL, Postgres. NoSQL was a relatively newer term and everybody used to be really excited and eager to learn about those things. I can recall those times that whenever we used to hear about Mongo, Redis, we used to feel really, really passionate about it. Fast forwarding now to 2024, the landscape is now completely different. You will find considerably large number of players out there. An interesting thing is that each database here has its own unique selling propositions. They are much more specialized and optimized to serve a special set of, you can say, use cases. If there is a real-time relational database requirements or transactions or atomicity need, we'll still try to use MySQL, Postgres. If there is a full text search use case, then it's worth evaluating ElasticSearch or OpenSearch or Solr. Similarly, Cassandra, MongoDynamo have their own use cases in the NoSQL space. With larger volumes of data, there's a need of data warehouse, and then and to generate reports or run through some computation. That's where likes of the Snowflake or Redshift come into play. The recent advancements and trend towards building Gen AI applications have reinforced the needs for vector databases. So vector DBs also exist as a category. In short, you can say any advanced and modern application nowadays would actually be powered or supported by many, many different databases. So what it means for an engineer, uh, we are kind of expected that we'll be interacting with multiple and often very diverse data stores. And it is possible that we might be interacting with multiple of them at the same time. For example, you might be uh, you might need to deal with NoSQL and Delta Lake together. Also, in today's landscape, we see extensive data movement happening between data stores. A common example is generating some kind of reports from an offline data warehouse and making it available for real-time use cases. The interfaces for these data stores are very different. They are not consistent at all. So there is a major challenge for an engineer to familiarize oneself with the data source that they are interacting with. And along with the interfaces, each data store has its own limitations and anti-patterns. So we'll try to take a look at a few of the data stores in next few slides. So the first one is Apache Cassandra, which is a wide column distributed NoSQL database. And it uses Cassandra query language, which is quite similar to SQL, but it isn't because Cassandra is not a relational database. So you won't find joins or foreign key. They won't be available in SQL. It is schema oriented, as you can see in the top right over here, where we are creating tables. We need to provide specific columns, their types, and whether it is a part of the primary key or not. The inserts and selects, simple inserts and selects are quite similar to SQL. Then another, my favorite data store is ElasticSearch, which is quite popular for full text search use cases. It offers a RESTful interface, which means you send out requests using HTTP protocol. It is document oriented, as data inside the engine is stored as JSON blobs. And it has its own specific query DSL language. For example, if you need to get all the data, all the documents inside Elasticsearch where a field named key has a value of 1, then you will have to define that criteria as the query, which is shown in the bottom right over here. Now, as you can see, if you compare it from Cassandra, the interface is entirely different. Now, the third data store I've chosen is Delta Lake. So Delta Lake is a data lake technology, and data lakes are actually repositories of data that contains raw data. So there is less organization in the data lake as compared to data warehouse. Uh, but the data Delta Lake actually offers an optimized storage layer on top of the raw file system. The underlying file system could be any of the uh, storage technologies offered by the cloud vendors like S3, etc. And one of the popular ways to interact with Delta Lake is through Spark SQL or the Spark Data Frame API. So we briefly touched about extensive data movement between different data stores. A common process for moving data is the ETL, which much of you are familiar with. So there are three stages. In the extraction phase, you need to know about the source of the data store that contains the right data, and then the capability of reading from it. The last stage is loading data, or actually publishing data uh, into the target system. And then there is a middle piece that comes into place which defines the logic where the data needs to be modified according to the business requirements. And that's the transformation stage. So in this picture, as you can see, that within the transformation stage, it is possible that there might be joins happening across, you can say, data from different sources, in between different sources, and then a completely different data format is created, or a completely different view of data is created and then pushed into the target system. So now let's consider a scenario where we would like to move, or we would like to build an ETL, a simple ETL pipeline where some data from Delta Lake needs to be moved to Cassandra. Now, recalling the different interfaces, it's a really challenging task to do it, because if we think the complexity, the engineer first needs to understand the format of the Delta Lake, read through it, and then do some transformations, and then need to learn about the Cassandra interface as well. And then they have to publish data according to that standard. So that's where Apache Spark comes to rescue us. But the question is how Apache Spark makes it agnostic. And for context, Apache Spark is a large-scale data processing engine. It supports a large number of programming languages like Python, Scala, Java, and R. But we'll more focus on the Python aspects here. One of the things that I really like about Spark is the extensive capabilities that it provides through the Spark connectors. Now, these software pieces would hide or abstract away all the complexity of the databases, and they would just present a a generic interface, which we can say a Spark interface for an engineer. Again, these connectors can either be built into Spark or third-party connectors that are developed and maintained by the database authors. For example, if you see over here, the Cassandra Spark connector is maintained by DataStax. That is the company which looks after releasing Apache Cassandra. Now, when you take away the complexity of the interface, an engineer only has to focus on the computation or the transformation logic. As a result, it increases the developer velocity. It improves overall engineering efficiency as well. So overall, the process to interact with any data store becomes really simple. What you need to do is to load Spark connectors, which are typically provided as Java packages. So if you are using a third-party connector, you'll have to load them. Along with loading, you will also have to make some configurations, and these configurations would include there are like two types of configurations. One is Spark specifics, in which you define the number of parallel workers or executors that will be running through the computation, and the resources for these executors as well. The other thing is related to these connectors, where you will be required to set some properties which are specific to particular databases. So we'll take a look at it shortly with some examples. And yeah, the final step is about reading or writing to these data sources via the Spark standard load and save constructs. So it remains consistent regardless of what database you are using. So now let's try to see how the same task of moving data between two data sources can be performed via PySpark. And how does a PySpark script looks over here? So this is a Python snippet. The first thing that is involved here is initialization of the Spark session. And Spark session is the entry point of a Spark job. And it is required to be initialized before. So as you are creating the Spark context, it is important to look at the way different jar packages are loaded over here. So as you can see over here, we have named the Spark session as PyCon PK24, and here we are loading both the jars associated. One of them is associated with the Delta Lake connector, and the other one is the Spark Cassandra connector. So if you want to use the Spark CQL interface instead of the data frame ones, then you would also be required to use SQL extensions. These SQL extensions enhance the capabilities of Spark CQL to support database-specific features. A common example could be any specific database constructs. For example, in Cassandra, there is a concept of TTL, setting up of TTL or fetching TTL from the database. So This TTL functionality isn't natively available inside Spark CQL, but with Spark CQL interface, you can then uh, with the Spark CQL extensions, you can use those. And lastly, within the Spark session initializations, you can see some catalogs which are being initialized. These catalogs, you can consider them as metadata repositories that it contains information about respective tables and their schemas and what are the different types of the columns in those tables. Yeah. And once we have set all those properties, we can just create out Spark session. So once we have the necessary scaffolding done and preparation done, now it's time to perform the ETL operation. The data here can be loaded into the Spark's data frame via the load API. By the way, data frame is just an immutable data structure of Apache Spark. And when you have loaded the Spark connector, if you look closely, there is a delta string which is passed inside the format API. And this is actually instructing Spark to utilize the libraries exposed by the Delta Lake connector in order to read data from Delta Lake. Yeah. So Spark will use all the optimizations which have been provided inside that connector library. And as an argument to load, you can see that we are providing a path where the Delta Lake tables are actually located. And in a real situation, it's usually a cloud storage locations, over any of the cloud vendors. Now, in the transformation phase, you can perform the computation depending upon your business logic. There can be now the transformation could be as simple as shown over here, where we are doing filtering based on a criteria such that the ID column should always be less than 100, and then selecting only a few columns with there might be like plenty of other columns available, so only selecting 2 of them. And once we have this transformation, the data frame which is created, now that's ready, and we are ready to publish this data frame into the respective data store. So as you are now looking to write to Cassandra, a few things that needs to be configured here, which includes the contact point, the key space, which is an equivalent to database in RDBMS, and then table where the data needs to be written. And similar to the reads you see during the write phase, the format specifically tells that it is Cassandra. So Spark will use the third-party Cassandra Spark connector for publishing data. And once you have completed all the actions, you can tear down the Spark session. And if you see that irrespective of the data store here, we don't need to worry now about the actual interfaces. We are not using any CQL statements for interacting with Cassandra here, because all of that stuff is being done by the Cassandra Spark connector. So in this way, you can use any data store over here, and you just need to have the respective connector. That's important thing. You need to you need to set some metadata which is quite specific to that particular data store. And lastly, you just need to call the Spark load and save methods on top of it after setting up the formats and stuff. So in this way, you can build out a completely data store agnostic ETL pipelines without worrying about to learn many new data source specific stuff. Yeah, thanks everyone. With this, that concludes my slides. If you have any questions, feel free to ask.
Junaid, can you hear us?
Yeah, I can hear.
Can you hear now? Can you hear now?
Yes, I can hear.
So we are just starting the question and answer session. We have our first question.
So hi Junaid, quick question. You say that you're using connectors within Apache Spark to connect to different databases, different data sources. So generally, what I've seen in enterprise solutions, they use ADF and its connectors for ingesting data and putting it back into let's say the decision system, right? So what do you see as the advantage of using Apache Spark over ADF for data ingestion, and then obviously for data dumping into the source as well?
Okay. So I actually, if I understand your question, I'm actually not aware of the enterprise solutions, one thing, but I can just compare briefly that I think it's the nature of the organization, which kind of you can say will help you make a choice whether you want to follow the open source path versus following, you can say, or tying yourself with some kind of vendor. Well, there are both the benefits, both the pros and cons of both the approaches. So the open source option will allow you to maybe be more flexible, but you won't have any support. So any issues or any stuff that you face, you have to do it yourself, and then you might have to build things by yourself. On the other hand, an enterprise version might be more costly, but you can get some better support around that area. So it's a kind of there are both positives and you can say negatives in using any of the approaches.
Okay, thank you. Anyone else?
I can hear you.
We just have another question.
Mm-hmm.
Hi, Junaid. So I had a question that, for example, in AWS, we have glue jobs that on the back end make all those PySpark, configurations and things itself through drag and drop. So what is the use case for this? Like how at a industrial level, how much do we need to know this tool and have to work with it manually?
Mm-hmm. Mm-hmm. So I think one thing is glue jobs work more or less within the AWS ecosystem only, right? And even for example, in any you can say complex, you can say software applications, you might not have all the components hosted on AWS. That's first thing is based on. So you could have some of the databases which are self-hosted or managed by yourself, and some stuff, for example, you are using by the cloud vendor. So the problem happens that the glue has a pretty, you can say, limited scope as compared to Spark, which is kind of open source. So if, for example, you need to do data movement in between Redshift and S3, then yes, maybe Glue Jobs would be a better option. But for example, if you want to, if you have a self-hosted Redis or maybe Cassandra or Elasticsearch, and you want to maybe move data from S3 to these data stores, then Glue might not be a better fit in your case. So again, you will have to choose. Maybe you'll have to look around how many different types of, you can say, target systems and source systems that you have for your use case, and then worth evaluating like which tool to use. An interesting thing is, like, because the scenario now in 2024 is too much complex that there are not like only a few target systems. There are quite a large number of target systems, and then looking at those target systems and also which new target systems that you think will be introduced in future for you. Considering all those, you'll have to then make a choice whether it's you want to use Spark, or maybe you can just opt for Glue if it's only AWS technologies that we need to work with.
Right.
Hope I answered you.
Yes, it did. And just one more point. The data frame that you mentioned in Spark, is it the absolute same data frame that we get from Pandas, or like there's something fundamentally different in it?
Sorry, which data frame you compared actually with?
From the package Pandas of Python.
So it's like it's the same concept around that, but Spark and there is like compatibilities which can be which is actually available in between those. But the Spark data frame is distributed, whereas Pandas one is kind of, you can say, host is inside you can say on a single host. So the main difference is kind of, you can say, the distributed nature of Spark's data frame as compared to Panda.
All right. Thank you so much.